You missed me singing. Those of you at home. We have the page 233 in your purple packet. You might notice that there are 4 squares here. Let's just go ahead and add a 5th because we're actually going to take 5 days. I've got the dates on the board right now. If you're playing at home, the dates might change, so I'm not writing them down. But here we go. Right now we're starting on the 25th. It's going to leak over all the way into another week or so. We have a teacher workday this Friday. We have a teacher workday on Monday. I don't know if you've noticed, but like the past several years, April Fool's Day has been a teacher workday. Just I don't know if that's on purpose or what. Yeah. Aren't you glad you pay it? Yeah. So, and you'll also notice that the schedule says things like this. SOL practice. That is not the case anymore. We're not going to be doing lots of random SOL practice because we were just discussing how the requirements have changed and almost no one is taking the SOL except for the few privileged. All right, so back to it here. Take a look at the vocabulary down there. Before we get to the test, make sure you know all of these terms. I say this each test, and I think a lot of people are kind of shocked when they see things. But you need to know what reaction rates and kinetics are. That's actually the focus of the chapter, so you might not know that yet. Exothermic, activation energy, catalyst, you probably heard about a little bit in biology. We'll go a little bit deeper on that. What are the factors that increase reaction rates? What the heck, a reversible reaction? That's new. And Le Chatelier's principles. We'll be going over these new and exciting terms in this chapter. There are some videos built into this. I'm not going to play the videos if you're at home. Pause it. We'll watch the videos here in the classroom, but you guys at home can just like Google where it says Iodine Clock or whatever. Just a second. So there are a lot of different iodine clock demonstrations out there. It's called the iodine clock because when you mix the solutions together, there's a precise time at which it changes. Now, if you change the molarities, concentration, how concentrated it is, it does change the time. So this chapter is partly about moving everything around and getting you dizzy. This chapter is partly about reaction rates, how fast reactions occur. That's a big part of it, is the speed of the reaction. It's also about something called equilibrium. And equilibrium probably means balance to you. Does it mean balance to you? In this case, it's not the traditional balance, it's about the rates being in balance. So you have reactants and you have products, and typically we just think of the reaction as going to the right, don't we? Reactants make products. But in reality, products can sometimes go backwards and make products. There was a sneeze in the room. Multiple people said bless you. And the reaction can go both ways. The most common example is this one here. A bottle of water that is sealed. Does it have evaporation occurring in the bottle? Do you sometimes get condensation on the side of the bottle near the top? Is it going back and forth inside? Yeah. And it's a sealed bottle, so you get both evaporation and condensation. But if you take the lid off, you no longer have a sealed system, and the evaporation can escape, and you might not get the condensation back, right? So one of the keys to a lot of our lab conversations and our math is that the system needs to be sealed up for equilibrium to be achieved. Now, equilibrium is also often tried to apply to like the entire world, but the world is not a sealed system, is it? It is actually a wide open system. We're constantly venting gas to the outer space, and it's a way too complex of a system to apply a simple perspective to. But, all right, next slide. These energy diagrams, I don't think we've seen them before. You have pretty much the same thing in your notes, right? Let's kind of go through them and explain. We haven't seen these yet this year. There's 2 different graphs there. Both of them start at the beginning. This is the beginning of the reaction. This is the end of the reaction. This is the beginning of the reaction. This is the end of the reaction. And they both, of course, start with reactants. And then when the reaction is over, things have become, yep, at the end they've become products. Now, I don't know if you can tell, the reactants start higher on this one and lower on that one. And then the products lower and higher. This is an example of two possible scenarios. The first scenario, maybe you're burning something. You're doing what's called a combustion reaction. So when you burn things, there's lots of energy given off, isn't there? Yeah, lots of energy is produced. And if you compare the reactants, maybe your notebook or a piece of wood or something, to the ashes afterwards, the ashes have a lot less energy. True? The ashes, all that energy has been released, and we call that an exothermic reaction. This first reaction is exothermic. Energy is released. Sometimes people say produced also. So it gives off a lot of energy. Any exothermic reaction you're around, you hold your hands over it, the reaction feels warm because it's giving off energy. The second one, the reactants start low and the products finish higher. This is an endothermic reaction. And probably the reaction you most identify with this would be photosynthesis. In photosynthesis, what are the chemicals that are combining? What are the reactants? What is it? No. What do they start? What? Sunlight, water, carbon dioxide. So plants take carbon dioxide and water and sunlight, put it together, and they make leaves, glucose, sugar, all sorts of complex things, right? And the products afterwards have more energy. So they take energy in. Those reactions are endothermic. So energy in this case is absorbed, right? It's absorbed or taken in. And the chemicals that are produced afterwards have a lot more stored energy, which we then break down when we burn them again or react with them somehow. Both of them have the hill, though, don't they? They both have that hill you have to get over. That hill is called the activation energy. So you put those reactants together, and they're colliding and colliding and colliding and colliding. They might not have enough energy. Is there enough energy in the room for the paper you're writing on to catch on fire with the oxygen that's in the room? There's not enough energy right now, right? We have the paper, we have the oxygen, we just haven't climbed up the hill far enough for the combustion to occur. So usually we light a match and we bring the energy to get it going, don't we? If, however, you warm up paper, I think the temperature is 451, 452. What's the book? Fahrenheit? 452, 451? I can't remember. It's the temperature at which paper spontaneously combusts, lights on fire. So if you crank your oven up to, let's say, 500, which is way above it, put a piece of paper in there, it'll catch on fire after a minute. First, the water will get evaporated out. There's water in your paper. It evaporates. 451? I was close. I was around it, right? So first the water evaporates, and then it will catch on fire after a minute. Even though there's no direct flame being put to it, you're just increasing the energy until you cross that threshold, and then the reaction can occur. The oxygen hits the paper with enough energy to break it apart and catch on fire. I don't know if any of you guys did like a project in elementary school where you had to make paper look old. You like dye it and stuff, and you put it in your oven and let it cool and dry it out, that is. You can make it look crinkly and old by a little bit of tea, and it gets really crinkly in the oven if you leave it too long because it dries it out. Both of these have an activation energy, a peak that must be crossed. Regularly things collide and don't react. One big idea, though, is that molecules must collide. If the oxygen and the paper don't meet, they don't react. If they don't have enough energy, they don't react. So there's a couple things that have to occur. They have to have sufficient energy, and that energy is called the activation energy. But more importantly, they must collide. If they don't collide, they don't react. And I have two really boring videos I'm not going to show you where there's slow motion, something goes and collides. It takes about 5 minutes for the collision to occur. So there are 4 things that impact a reaction's speed. Concentration. Higher concentration versus lower concentration. Which one do you think speeds up a reaction? High or low? High. If it's really concentrated acid, it's going to react really fast. If it's low concentration or dilute, it's going to react really slowly. Temperature. Which do you think would speed up reaction? High temperature or low temperature? High temperature. Usually at the end of the year, we do a bunch of outside demonstrations, and you all are in the 3rd block of the day, so it works really well by this time. Because at this time of day, it's usually about 80 in June, and when we go outside to do this, the temperature actually speeds up the reaction. And it usually takes about 4 or 5 seconds. We mix this syrupy stuff with a black powder, just mix it together, walk away, catches on fire. But in the 1st block of the day, do the same thing, mix it together, 4 minutes later it catches on fire. Because it's so cool in the morning, it's only like 70, the reaction really takes a long time to spontaneously combust. It's a pretty cool reaction. Surface area. Which do you think would react faster? Like a block or a powder? Powders react way faster because all of the particles are exposed. They're all exposed. And then there's a catalyst. You guys have probably heard the term catalyst before. A catalyst. Oh, you're reading? Breaks down the enzyme? That's pretty good. That's not up there. Yeah, it speeds up a reaction, but it does it by lowering the amount of energy that's needed. We're going to watch a video by TED Talks. You know the TED Talks? You ever watched TED Talks? This is a dating analogy. For those of you at home, you just Google TED Talks dating analogy and reactions and stuff like that. You'll get it. Yeah, when you grind up a solid, by grinding up a solid, you're exposing all of those little atoms that are clumped together. You probably do this at home with like a salt grinder or something like that. You don't put chunks of salt. You put ground up little pieces of salt on your food, right? Salt grows naturally in huge cubes, and we usually grind it up and spread it out and stuff to spread out the flavor. So on this graph, I think in your notebook it's missing E. Can you add E on there? Is that missing? Yeah. All right. Add E, and then I'm going to add another question in a second. So the first one, though. What letter is the delta H, which is heat of reaction? That's what delta H stands for. And that would be B. B represents the heat of reaction because it's a comparison of before and after. Isn't B the difference between the before and after? And so that's the heat of the reaction, how much the reactants versus the products change. Which one is the original activation energy? That's what that means. Activation energy. It's actually D. It's the higher hill. The higher hill is the harder one to get over. C represents if you add a catalyst. All right, if you add a catalyst, that's this here down here. I skipped one, but if you add a catalyst, it lowers the amount of energy you need, which then makes the reaction go faster. And then energy of the products would be A. And let's also add energy. Oh, handwriting is amazing. Energy of reactants. And that would be E. The energy of the reactants is E, where the energy of the products is A. And so if you're at home, you know, you're putting in energy, bang! And a lot of energy is released. Versus putting in energy, bang! And not as much energy is released because you didn't have to get up quite as high. Yeah, that's the activation energy. My handwriting's not the best. Yeah. Looks like I got a C in handwriting, sorry. At least I can make the letter C though. That's good. Sort of. Okay, no, it was not a good C. That was kind of the part. Yeah. Equilibrium condition. So, some reactions are reversible. And this is where it gets a little weird. We've seen those arrows, I think, once or twice where they're going both directions, where A makes B, but B can also go backwards and make A. Some reactions are reversible, and they typically have a double-sided arrow. We'll see this type of arrow. My pen. We may also see arrows that look like this, which is also a double-sided arrow, but it's like a weird, lazy, odd double-sided arrow. It's the same idea, just the reaction can go both directions. The key is that as the reaction is occurring, and here on the picture we've got some of this compound, and it's reacting, and the amount of it is slowly decreasing. And what's happening to the products? They're increasing. And we reach a certain time in the future, and at this time, the amount of product and the amount of reactant is no longer changing. And what's weird is both of them are there. And the reaction hasn't actually stopped. They're just occurring, and this is the key, the reaction is occurring at the same rate. As it's going forward, it's also going backwards at the same rate, in balance, if you will. That's why it's called equilibrium, because the reactions are in balance with each other. We typically do a little bit of math equation setup here, where you guys get to set up the equation. In order to explain it, though, let's review a couple things. On this side, what do we call A and B? Are they the reactants or the products? They're the reactants. What do we call C and D? The products. And then last chapter, we saw things in molarity, in brackets, right? And again, anytime you see something in brackets like this, that means molarity. So if you were to come along, Jeff, was it? No. Phil. If Phil was to do this reaction and measure the amount of products and the amount of reactants and write it as a ratio, he would always get the same answer. And when you get a number again and again and again, you eventually give it the constant status. You say it's a constant. And so people measure equilibrium when the reaction no longer appears to be moving, and they write the ratio of products to the ratio of reactants. You know, there's 15 moles per liter of product. There's 3 moles per liter of reactant. What is 15 over 3? 5. And so that ratio is a constant for that fake reaction I was just saying. And the symbol for constant is, of course, K, because that's how you spell constant, with a K. Right? I think in German, I think it's constant. But that's not true either. Let's just do an example here on the board. What are the products in this reaction here? The 2H2 and the O2. And then the 2H2O is the water. It's the reactant, isn't it? Right? So the way this one would be written is like this. The products over the reactants. H2, O2, and water on the bottom. And I'm going to emphasize something. This 2 here, that coefficient, you see it's becoming an exponent, isn't it? And that's where this chapter gets a little weird. This 2 here is also an exponent. What's the exponent for the oxygen, the O2? It is a 1, but we don't really need to write down the 1, do we? So it's often left off. I have typically in the past yelled at this point. Would you like the yelling version or the like just quiet I'm paying attention version? They want the yelling version. Those of you at home, so you see how this is addition, but here it's multiplication. That's a little confusing, so I usually like to overemphasize that. and I say where it's addition here in the expression, it becomes multiplication. And then one or two people, maybe they catch on. This is not actually addition. It's not actually the math addition like we have in our math class. We're just saying these two things both exist on one side of the reaction. These things exist on the other side. Whereas in the expression, that addition actually becomes multiplication. All right? That can be a little weird. Now what I want you all to do is I want you to try to set these up. What's the product? What's the reactant? I can go back, yeah. So the products go on top, the reactants go on bottom. If it has an exponent, it becomes, if it has a coefficient, they become the exponents, right? So try the next two examples that are there on your paper involving oxygen and like hydrogen and fluorine. Try to set those up. I'm going to pause here. The products go on top. If they have an exponent, or if they have a coefficient, that becomes the exponent. So this 3 came from that 3 right there. This 2 is from the reactants having a 2 in front of them. Yeah. Now we have it set up, and then when someone, say Phil, runs the reaction, and after 20 minutes the reaction reaches equilibrium, we could plug numbers in for the reactants and calculate K. And that's going to be the next step in a second. And a K for that reaction will be a constant. Timing out. Okay, try that one during this timeout. So this is a little weird, right? We have the products squared, the reactants multiplied. Not added, but multiplied. And we pointed out these would be 1, so this would be the first power. Do you need to actually type into the first power if you were using a calc? So then the next step in the process is, say you've got it set up, and then we hand hydrogen and fluorine to Phil, and Phil runs the reaction. We come back 30 minutes later, and he tells us the amount of hydrofluoric acid, hydrogen, and fluorine, and then we plug them into the expression. And Phil, give me some random numbers. 5. Give me 2 more random numbers. 3 and 2. Okay, so these are all fake numbers. So he says the reaction's over, and for hydrofluoric acid I have 5 molar, and for hydrogen I have 3, and for fluorine I have 2. And now could we solve that math problem he just created? What's 5 squared? So we have 25 over 6, right? And that would represent a constant. But it starts off with, did he set it up correctly? And then did he plug the numbers in the right spot to solve for the constant? Which is our next example. All right? So in this example, first let's set up the expression. Let's go over there to Nike. Nike, what would be the expression for this reaction? SO2 exponent 2, yep, times oxygen, O2, right? SO3 was the 2 of the exponent. So we have the setup. Now what we're going to do is we're going to split the class in half. If you're in these 3 rows, all right, that's from Phil over this way. You guys are in experiment 2. And I want you to plug in these numbers into the spot. So for SO3, you plug in 0.26. Plug in, plug in. And then the other 3 rows, all right, you all are experiment 1. Plug in your data, and let's compare our answers in a couple seconds. So there's several different ways to solve this. We plug the numbers into the correct spot. That's a huge mistake people make on a regular basis. They plug the number in the wrong spot. You just set this up. You said that's squared. When you plug the number in, make sure it's still squared, right? You said that this thing's going to be squared. Make sure when you plug the number in, you don't lose that squared. I clearly yelled at you and said, this is multiplication. It's still multiplication. You do have to maybe add parentheses on the bottom so that the entire thing is still in the denominator. Or, as Jilly told us, she does the top. She does like 3.5 squared, writes it down. Then she does the bottom, writes it down. And then she does the top divided by the bottom. Can I get a couple people to tell me their answers? What'd you get? I got a 4.3. And what about from team 1? So I don't know if you remember this, but K stands for the German word constant. That value should be constantly the same for the same reaction. So if one group got 4.3, the other group should also get 4.3. They should get the same answer, even though the data is different. Isn't that funny? The data looks really different from each other, but the answers are the same. You would never look at these two sets of data and imagine that the ratio was the same, because it looks such drastically different data. But it is. They're both 4.3 over 1 when you simplify it down. So with these weird reactions, these equilibrium reactions, as the reaction proceeds to the end, not everything's actually gone. We still have reactants and we have some products. And when it stops reacting or reaches equilibrium, there's a ratio achieved that's unique to that reaction. So for this reaction, SO3, SO2, and O2, that ratio is 4.3 over 1. 4.3 over 1. And it always stops at that weird ratio. For the reaction I have below here, it looks like the ratio all 4 times is about 0.21. It's a different reaction, so it has a different constant. Yes, Philly. Oh, plenty. Yeah, or if I had given you this data here and hadn't given you, say, this, we can solve for that missing piece because we know that K and K have to be the same, don't they? Because for any given reaction, there is one constant that is the constant for that reaction. So if it's 4.3, it's still 4.3. And we could solve for the missing piece, for instance. Okay? That's a pretty good question, Philly. I'm proud of you. Some weird things that actually make it easier. If you have a solid or a liquid, solids or liquids get replaced with the number 1. They actually get to be a lot easier mathematically. So in this expression here, we have originally would have K times CaO and CO2 would be multiplied together over CaCO3, right? That's the initial move. But anytime you see a solid, you replace them with the number 1. What is left over after you replace the solids in this example with the number 1? Just the carbon dioxide. Yeah, you got it, Ali Weissa. Yeah, just the carbon dioxide, because this is a solid, so it gets replaced with a 1. This is a solid, it gets replaced with a 1. And I really struggled with why the heck are we replacing these things with the number 1 for a long time. And then it kind of, it took me 15 years. I'm just going to skip those 15 years and get to this point. This is really about speeds of reaction, right? Which moves faster, a solid that's sitting still or the gases that are flying around them? The gases. The gases fly and hit the solid. What if there's a lot of gas? More hitting, right? And it's really about how much gas there is, not about how much solid there is. So if you change the amount of gas, you change the amount of reaction rate. And that's really what it's based upon. This is hitting my beard, which really creates some interesting when you listen to it. The same is also true for liquids. We don't treat liquids as if they're important because they're moving so slow compared to gases. Just as a point of reference, gases move at 240 meters per second. The gas in this room. The solids don't move, do they? So in terms of which impacts the speed of the reaction, it's really the gases. Liquids do move, but compared to 240 meters per second, they don't move. So the liquids don't get factored in either. So this one, the liquid over the gases. Now Donnie back there in the blue hoodie, Donnie would like to point out that we've already done this reaction. Yeah, that's you. That we've already done this reaction, but earlier this was not a gas. It was this was a gas and not a liquid. So it was included because it was a gas. Yes. It's not an L. That's a 1 squared. Solids and liquids get replaced with a number 1 because they don't impact the speed. They don't impact how fast the reaction's moving. If you double the amount of solid, it doesn't double the reaction because you're still really waiting on the gas to hit it. All right? Solids and liquids are replaced by 1. Yeah. I got, yes, VCU. Ali Wysa. The CAO? That's okay, yeah. I'm looking at the subscripts, the solid, liquid, gas part, yeah. I forgot to emphasize that. Good catch. Donnie, did you have a question? If you have aqueous things floating around in water and other aqueous things floating around in water, you're waiting for them to collide in the water. So they might get represented in here. But if you're talking about a solid that's not moving and a gas that is, you're really waiting on the gas to hit the solid, not the other way around. So you change the amount of gas, you change the speed. All right. So here's an example where we're kind of applying some of these ideas. We write down the expression K equals H2 squared times O2 divided by, does the water get included this time? Is it a 1 or does it stay? It's H2O gas, so it does get included because if it's H2O gas, it's flying around, moving quickly, and it's going to actually impact the speed. And it should be squared, shouldn't it? All right, so now that I got the setup, I'm going to plug in the things they've given me. They've given me K this time, haven't they? So we know K is 2.4 times 10 to the minus third. What else do we know? We know the water is 0.11 squared. We know the hydrogen is 0.019 squared. We don't know the oxygen, X. Cool? So we have to solve for X. We have to do a little bit of algebra and solve for X. I'm going to pause while the algebra occurs. So I cross-multiplied the 0.11, and then I divided the 0.019, made sure they were both squared, and I got X equals 0.0804. So since X represents the amount of oxygen, that should be the amount of oxygen. Well, I plug the numbers in. I don't know oxygen. So how do I solve for that? I cross-multiply the 0.11, and then I divide the 0.19 underneath, right? Just setting it up so that I plug the numbers in the right spot. It's knowing what my equation is. If you plug them in, like you could do, a lot of kids do this part in their head. Yeah, Donna, you're right. Some kids do that part in their head. They're like, you know what? That's going to be K, that part's going to be squared, that part's going to be squared. I don't know that value. And you could set it up in your head and throw the numbers on paper. I prefer that you write down the equation. That way, if you forget an exponent, I can help you out. I can point it out. All right. Same thing's going on with this one. We're going to write down the setup. K equals N2O4 over NO2 squared. Let me move the board a little bit. There we go. And what do I know? I know K. That's 10,000. 10 to the fourth. And I know if I plug in X in here, I got to make sure that X is still squared, don't I? Because it's NO2 squared. So this is X squared. So I would switch the places of the X and the 1000. Yep, it's just algebra once you set it up. So I got X squared equals 4.5 times 10 to the minus fifth. Have I finished the question? I've got X squared. How do I solve for X? Yeah, take a square root of both sides. And I got 0.0067. All right. So 0.0067. These are the harder ones where you have to set it up, plug it in, and solve for a missing component. I mean, solving for K is kind of the same, but K is on one side and the components are all on the other side. And these two examples, you knew K and you were missing one piece. So from a chemist's perspective, why is this useful? So Jilly wants to make something, and if she knows the equilibrium constant is, say, 10,000, she can predict how much N2O4 she can make by mixing NO2 together. Consistently predict it because she knows it reaches that value. All right, and chemists, especially organic chemists and factories and things, take advantage of a lot of these scenarios. The last little piece in the notes is not math. It's actually about how things react. So let's say that Aloysius here had a system that was in perfect balance. There were some reactants and some products, and then Billy comes along and starts changing the scenario to mess up Aloysius's balance. And there's some things that you could do. These names are just ridiculous. This reaction is in perfect balance. It's in perfect balance. The amount of carbon dioxide, the amount of carbon monoxide, the amount of oxygen. It's going back and forth, and nothing's changing. And then someone comes along and does this. And I usually visualize a whole lot of CO2. Is that still in balance with this huge extra amount of CO2? No. What do we need more of? The other side, right? So all we do with this, we go, wait, if there's extra CO2, we need more stuff on that side. We need more stuff on the product side to get it back into balance. This is all about kind of like the old seesaw. If you have something, two small things on this side could equal one big thing on the other side, right? And getting them in balance. Well, what if someone comes along and let's get rid of this big CO2. It gets back into balance, and then a new person comes along and adds a whole lot of extra oxygen. It's not in balance with extra oxygen, is it? Which side do we need to add to get back to balance? The reactant. So it needs to go that way. We need to add stuff to the left side to get it back to balance. All right, and then 5 minutes later, it's back in balance. And then Donnie comes along, and Donnie removes the carbon dioxide. He steals it. Is it in balance if these things have been stolen? No. Which side do we need to add to? We need to add to this side, don't we? And that's what these problems are, is about looking at which side it needs to shift to balance back out. Let's remove Donnie's chicanery. And removal of CO. That side, what happens to that side of the reaction if the carbon monoxide's gone? It's unbalanced. The oxygen doesn't have anyone to react with, does it? So this side of the reaction stops. That side's still going. We need to add to the right side to get it back into balance. This is what Le Chatelier's principle is about shifting. That's called shifting. It's going to shift to the right or shift to the left. Not like that, shift to the left, not that. It's going to move one direction versus the other direction. Oh, thankfully one direction shut down. I'm glad they're gone. But, sorry. It does get a little bit more interesting, but we're almost out of time, so I'm just going to pause here. We'll get more into some of the other Le Chatelier's stuff with shifting in temperature next class. We're pretty much out of it. And one other really important thing I have